the organizers. Yeah, so I'll be talking about slightly non-standard approach to the S-matrix that is nicely geared towards flat S-matrix, geared to the asymptotic symmetries, possibly holography. And that's based on this work from last year with Solwa Kim, postdoc, former postdoc Ruben Monton in the audience, and another student Richard Myers. And then the second half will be about sort of incorporating this into an old subject, which is the S-matrix, flat space S-matrix and flat limit of ADS. And this fits in nicely, and that's stuff that should appear here with Richard Myers. Okay, so let me just jump right in and think about how to a different way of deriving expression for the S-matrix. So let's imagine you had some non-standard education and you learned about ADS. You learned about like the GKPW dictionary for ADS. So you knew GKPW that you're supposed to look at ADS with some boundary conditions. Phi goes to some sources at the boundary, and then you're supposed to compute the ADS of J, and this thing is then the generating functional of boundary correlation functions. Okay, so now knowing that, let's suppose you ask for what is some elegant thing you might try in flat space. Okay, so let me, to be very definite here, I'm considering 3 + 1 dimensional. Could be asymptotically flat space, but for definiteness, just write down pure Minkowski space. And let me just, again, really just to make things as simple as possible, just consider a massless scalar field, real scalar field. Okay, so right, so we could start from the action. I'm always going to call this is always a Lorentzian action. I call it I because it's for S matrix, so not get used by that. And so some integral over Minkowski space and just some standard action, say some potential, and let me allow for the possibility of boundary terms, which someone versed in ADS would of course want to entertain. Okay, so let's write massless particles. So, well, first of all, the standard coordinates here. I'm just going to work in spherical coordinates, but then we find the null coordinates u equals t minus r, and so then we'd have minus du squared ddu dr squared, or the other guy t plus r, and then we'd have minus d squared plus d dr squared omega squared. Okay, and then we have usual picture for flat space. Radial coordinate going up there, t coordinate going up there, the null coordinate going there, and u. Okay, and so this scri plus, and then down here scri minus. Okay, so like in ADS, we'd like to imagine doing a path of this with some boundary conditions. Okay, so then the question is, what boundary conditions should we impose? So let's suppose we hit, so we're going to call phi bar. These are going to denote some boundary conditions yet to be specified. Okay, and so we're hoping to define and compute this partition function in asymptotically flat space as a functional of those boundary conditions. All right. Okay, so what boundary conditions? Well, first of all, I'd like to say about the asymptotics of the field. So we have a massless scalar field for the generic asymptotics for the kinds of solutions I'm interested in, sort of scattering type solutions. The field will fall off like 1 over r generically. And then we want to look at the asymptotics both on scribe and scribe minus. And so on scribe plus, there'll be some function, let me call it f plus of u and then the angles, right? So scribe, there's a u coordinate, and of course there's also the sphere, the celestial sphere, not displayed here, but those are the angles there. So that's on scribe plus. And then we have some corresponding function of v and omega on scribe minus. Okay, and in order to further the boundary conditions, let me go a bit further with it, because these are related to standard mode expansion of a field. So, of course, I'm going to be assuming that some interacting theory, but we assume I'm going to do a scatter. We assume that we've got infinity, the fields are effectively free. And so certain near infinity, I can do the usual mode expansion. Let me call this guy B. B dagger. So that's the typical solution. And it's important for me, I'm going to think of, as displayed here, splitting up the field to its positive and negative frequency components. So the first term here, this part here is the positive frequency part. That's the part that goes like some b and then some e to the minus I omega t. Omega, of course, is just given by that guy. So if over here is the negative frequency part, which goes like some b dagger plus I omega t. And okay, so then the relationship between this expansion and this 1 over r fall off comes when you evaluate this thing at large R in the saddle point. So it's kind of useful to see that. So let me actually write that down. So, so we're going to go to large. What we can do is write e to the minus I omega dt. This is 5. X, of course, but then rewrite it in our, suppose we're looking at this off at scribe plus. This minus IR P X like that. Towards scribe writing coordinates. And you can see here, if you go to very large R, this thing grows, and it's then you can do a saddle point approximation, and it really fixes this whole thing to be 0 and sort of pins the momentum direction to x hat, which is the location of the sphere. And so that, then you can do the integrals here in terms of t, and you will find that this thing here asymptotes to minus I over 8 pi squared r. That. Like that. So that's as you go off the scribe plus. And there's some very similar looking expressions. You go to I minus, is replaced by v. And so again, you can see here that the momenta there are being given omega, and the momentum is given by where you're heading, the location on the sphere that you're heading to. Okay, so this so these functions here that appearing here are one of our these guys, and so boundary data is going to be encoded in these functions, or alternatively in terms of the mode coefficient. Okay, right. So now, good. Let's come back to boundary conditions. So what do we want? Boundary conditions in general. Well, we like boundary conditions to uniquely specify some classical solution of the equations of motion. We should do. And so if we're just doing ordinary time evolution, of course, we might just specify the whole field here. Okay. But I want to do something more akin to the S-matrix. So we want to treat past and future more democratically. So instead, I want to impose basically half of the data in the past, half of the data in the future. And as I already alluded to, the natural way to split up the data is in terms of positive and negative frequency parts. That's really the only natural splitting you do often if it's past and future. And so right, of course, it's spatial infinity. And here we're working on, these are Cauchy surfaces. Oh, if I want to specify the state, yeah, that's right. Yeah. I cap it off like that, if you're saying, indeed, yeah. So now you might naturally put in vacuum there and then just put boundary conditions here. That's right. So, I mean, the analogy is perfect. It's a different situation. But yeah, right. So this is just right, so we put boundary conditions here and use something like this. Then of course you're computing in amplitude in the presence of a source. Okay. Yeah, if you took the limit with some I epsilon type picture. Yeah, 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 yeah. Set the size to infinity. Yeah, yeah. Well, I mean, I'll essentially that's yeah, yeah. Well, I think if you took a finite size and it's in some order of limits type thing, you took an infinite length. Okay. Right. So what we're going to do is on scry minus, we're going to specify the positive frequency part. So I'm going to, I'll call, when I write phi 1, that means the 1 over r part field, that subscript there. And bar means it's a boundary condition, and plus means here positive frequency part. So there's some positive, there's some asymptotics go like 1 over r times this function, which is purely positive frequency in terms of v. And then here I'm going to specify the negative frequency part. Okay, and so get these null surfaces with limits of space surfaces, but yeah, at the end. Okay, so then good. So that's our boundary condition, and then of course we need a good action with a good variational principle, and so that's where the boundary terms come in. And so if we if we take the usual on-shell variation of, I mean, the relevant thing here is from that kinetic term, and so that's given by some 1/2 integral over the boundary metric normal. And this is just the on-shell variation, which is what I care about. Okay, and then right, then this has some unwanted piece by itself. So now I go and split up into the positive and negative frequency parts, and I want this to vanish when I don't vary the boundary conditions. That's what it means to be a good variational principle. So there's some unwanted piece here, and that unwanted piece, scry plus, and looking at scry minus. The unwanted piece is then minus 1/2. Plus. And since I'm holding the boundary conditions fixed, well, this delta here, this delta I can actually just bring outside everything. And then that means that I can cancel this by the action of this thing. Okay. And so let's call this whole thing, let's call that minus delta, then the natural inner product here by minus with 5 plus, and that's 5 plus. Okay, so the boundary guy, so this expression here is just defined by that thing, basically inner product. And so, and the boundary terms are, there's one on scry plus, and the corresponding thing on scry minus. Okay, so that's our action, and together, I mean, now often I write down, for the boundary conditions, I might just write down one phi bar, which is the sum of the positive and negative frequency parts. It's just some free field which is just designed, its asymptotics capture the boundary condition. They just capture them together as well. Okay, so correct, yeah. Mm-hmm. Yeah, I mean, it's right. It's right. You have to, yeah, it's positive frequency part, so it's yeah. Well, it doesn't worry me because it produces the answer I want. So it might worry in intermediate stage, but you could, you won't get the S-matrix, this theory, if you do that. So my sort of, what I'm saying here is you kind of follow your here, and what you land on this thing. Now we can, yeah, I'll give it other alternatives, but this will give the S-matrix. Actually, sorry, no, let me take it back. Sorry. This can be a look. So, sorry. I can, for free, see, I can add on the minus part because this will have vanishing inner product with this guy. So I could replace this by the whole phi. So sorry, it can be written as a local one. But yeah, it definitely is local. Unlike how they come through here. Yeah, it can be written manifested. Yeah, so it's a little bit hairy when it comes to gauge theories. In this case here, I can just say I'm going to restrict to nice wave packets and things like that to die off. So I'm okay with that. It's much more subtle when it comes to QED, when we have to worry about the long tails and so on. So fact, I don't entirely understand what the roots do that. Okay, so right, so we have this, and then we go and compute. We just so we do the path integral. We get this asymptotically flat space thing as a function of these boundary conditions, just by doing the path integral with this thing here, which in action depends on phi, and of course it also depends on the boundary condition. Okay, so what is this thing that you've computed? So one way to this matrix makes sense. But let's take the phi bar and let's convert it to an operator. So when I give the expansion, give a corresponding expansion like this for phi bar, and then promote b of p to some operator, same dagger, and these will just obey the usual commutation relations. Okay, and so if we do that, then this thing becomes some z hat of this operator guy. And now, of course, this by itself is completely ambiguous because it depends on operator. Let me do the following. So let me add in a term here which is subtracts off the boring free part. So that's just phi bar. So that's the part that I think boundary term. I stick both of these things to be the bar that just sets the whole thing to zero, the exponential to zero, when we that just so they want. And then I'll just normal order this thing. If operator and claim is that this thing is the S matrix. So the S matrix, which you think of as so these operators. And so it does what the S matrix do. If we have some collection of P1 out, P1 in, then this is equal to this operator here. Okay, or a bit more similar to what one does in ADS, one can think of this sort of more directly. This thing here is like a generating functional of this source phi bar. You can differentiate with respect to get the S matrix element. So then in this language, I could also get these S matrix elements by taking derivatives of dagger of P1 delta P of P1 dot of phi bar, and then set phi bar equal to zero. Extra kinematic zero, which I'm not really. Okay, so good. So I'll explain why this is true in a second, but anyway, it is true. It'll give you S matrix. Yeah. Well, phi I integrated over. So I integrate over all field configurations, the boundary conditions. The boundary conditions are specified by phi bar. And then phi bar, expansion of that form right there, and then I convert phi bar to an operator. Yeah, so that's what I'm giving over here. So this is the alternative formulation here, which is like ADS. This is now not an operator, function of C numbers, and I'm just differentiating respect to these C number coefficients. So that's like the source. That also gives you the same thing. So I can view it in that way. Yeah. So the answer also goes to yes. And I'll give you one example where this operator version is in a second. Yeah. But yeah, it's not a. Well, yeah. So I'm going to later directly. I mean, this thing actually has a very simple relation to the ADS partition function, and so you could do it there as well and generate corresponding. no, phi bar, when we embed the ADS, make the limit, the phi bar will actually become like the source. So it'll be a very simple relation between the ADS source and then this phi bar. Yeah. Okay. Okay, good. So why do I like this thing? So, well, of course, we should compare this to the usual LSZ formula where we have the same matrix element, same S matrix element. Right down here. So this would be just in shorthand, the residue then of some, correlators. This. Okay. So I'm not going to make any claims of computational advantage. The thing, so this of course based on you compute some local operator correlation function, and then the residue effectively takes the things off to infinity. This other formula sort of works with asymptotic boundary data from the get-go. So you never referring to any local objects, and so that seems kind of more holographic. It's also, I think, it's good for asymptotic symmetries. Symmetries act on asymptotic data, and this is the basic input. And especially in quantum gravity, you might like something that doesn't refer to local operators at some intermediate stage. You can direct them and so on. And we know in ADS, I mean, there are different ways to do correlation function in ADS. A general formulation in terms of the GKBW path integral allows you to do certain things. There's other, I mean, you can do things like localization and so on. Unrelated to the S matrix, other quantities. So formula things here in terms of S matrix may, in terms of the path integral, may allow things of that nature. Okay, before going on, I should say that so there's also this paper by Shiraz and friends a few ago that also looked at some S matrix in the path integral type formulation, although their emphasis is quite different. But we'll go there. Okay, this formula here is not new. Okay, so years. So this goes back actually to era Feva, the day of Slavnov, who very conveniently have initials that match. So thanks. That always tells you on the right track, and you get coincidences like that. And anyway, of course, they weren't thinking about these terms. They were doing stuff like the coherent state representation of the path integral, and you can arrive at this thing. And then the way the boundary terms come out in that way is but very different and super tricky and so on. But anyway, at the end of the day, it is the same expression, at least in cases that I know about. Well, they did consider, they were interested in massive, they do some discussion of gauge theory, so they include massless, but they basically put in like time space-like surfaces. Yeah, and not, yeah, so they yeah. Yeah. So then to do it nicely, what you should do is one of these things where you want to sort of resolve future in fast infinity. And so this is really done as these hyperbolic slicing. And so you can keep track of locations of particles, asymptotic. So here the momentum got correlated to the celestial sphere. If you do that thing, then the momentum gets correlated to some location hyperboloid. So it's a bit more complicated, but there's analogous version of that. Okay. No, I haven't thought about things from that point of view. I guess my main perspective here is to try to write things down in terms of a path integral with asymptotic boundary conditions. So to the extent that they're probably not doing anything for the path integral. Yeah, not. Yeah. you actually prove that this is correct. So in fact, I'll just sort of sketch it. Actually, the argument for why this produces the S matrix is very similar to the argument that why the two different formulations of ADS correlators are equivalent. So there's the GKPW prescription, the boundary conditions, and the source. And then there's like sometimes people call the extrapolate dictionary, or I think it was first appeared in the paper by Immel and Douglas and Horowitz, where you get a bulk correlation function, and then you take it off to the points off to the boundary for stripping off the prefactor. And well, those two formulas are equivalent, although for some reason there's not actually a clear explanation of that in the literature, why actually they give the same answer. But it can be proved the same way. It's all sketched right now. It's in our appendix, our paper we put in the argument for the ADS case. It's very, very similar. And so, okay, so equivalence to LSC. Again, this is just a sketch. But the way to do this is to, let's augment the action by now having both bound, so I'm going to same boundary conditions as before, but now let me also add in a source to the action. Okay, plus the boundary terms, and then I get the path integral with the boundary conditions and the source. And effectively, what I'm going to do to toggle back and forth between LSC and the formulation is turn one or two of these off, and then show that they're equivalent. And so first of all, so if you set phi bar equal to 0, so just have trivial boundary conditions, basically vacuum boundary conditions, then you just have the source. You're computing the vacuum diagrams with the source. So there are a bunch of lines, sources, and of course each line here is some Feynman propagator attached, and this would give me Z of 0J, sum of diagrams like that. And then, of course, we do the LSZ prescription. What we do is basically amputate the external lines after we go on shell, and then we replace those external lines by some on-shell wave function. And on-shell wave functions are basically captured by the phi bar function. Those are just plain waves, wave functions. And so, so I could say is that S LSZ as a function, this is a free on-shell wave functions, is basically given by this partition function, trivial boundary conditions, and a source. But then I'm supposed to basically take do this. So this means amputate the stuff, replace it by the on-shell wave function. That can be the LSZ expression. Okay, and so what you want to show then is that is this equal Z of phi bar 0. That's what I talked about before. I had no source turned on, I had the non-trivial boundary conditions. And a sloppy argument to that effect is that, so imagine computing things in perturbation theory. Imagine computing this path integral perturbation theory. If you want to do perturbation theory, what you want to do is you want to first solve the free equation of motion. So I'll put in a part here that captures the boundary condition. That's just the free field obeys the homogeneous free field equation. And then I'll incorporate the source just by Feynman propagator. It's of course very important here I use the Feynman propagator because this thing already has the right boundary conditions for positive and negative frequency behavior. The Feynman propagator is the one that has pure positive frequency in the future and pure negative in the past, and that's what doesn't mess up my boundary condition. So that tells me I have to use the Feynman propagator. It's not something I'm supposed to assume. Okay, and so if I do that, then I put this into the action, and then I expand around that. I write phi as phi bar j plus perturbation, and then I systematically solve for the perturbation. And think about that, how that works. You'll see that phi bar and j only appear via this phi bar j function. captured in the phi bar j, but then you do perturbation theory. The perturbation theory just sees the phi bar j as providing source to the equations of motion. But then notice that under this replacement here, this thing here, you actually get the same. So I can either set to 0 and then just have phi bar there, or I could set phi bar to 0 and then take this replacement GFJ goes to phi bar. It produces the same phi bar. Okay, so you can toggle between them. It's the same phi bar j, and so therefore the resulting functions are the same. Now, this is actually a bit of a lie. So there are some ambiguities in that that I don't want to get into, but you can prove it's roughly correct. There are some, there's actually, you can in principle get other things appearing. You toggle back and forth between the two cases, but a few more arguments show there aren't such ambiguities. So that's with some extra steps, that's the basic idea. Okay, and as I said, a similar argument applied showed that the DPW and the extrapolate dictionary for correlated data. Okay, by the same token, the reason, so this is proposed 50 years ago, essentially. It actually appeared in some textbook, sort of in the parts that nobody reads, but it's not, the reason it's not typically computationally useful for the standard calculations. And as you find, if you perturbation you carry out here, when you're doing something involving Feynman diagrams, not surprisingly, what you end up doing are Feynman diagrams again. And so to officially calculate it, it's basically the same thing you'd normally do anyway. But my point here is to not focus on standard amplitudes, but more on the asymptotic symmetry point of view, where these things are something like that. Okay, so let's see. Do I want to? Okay, so here, just time. Yeah, well, here's one fun example which I like, where this really is more useful. And so let's just consider the free case, free field theory. Now, if it's a pure Minkowski space, that wouldn't be so interesting. But let's look at a free field in curved space. So imagine I had some thing like this, but in here I have some non-trivial metric. Okay, so asymptotically flat, non-trivial, say time-dependent metric. And so even some free field, I'll have a non-trivial S-matrix and particle. Okay. So this is, of course, a standard problem, usually solved by using canonical methods. But here it's incredibly good to answer. And so the way you solve this, write down two sets of mode solutions. So you write down one set of mode solutions, u sub I, which are positive frequency on scribe plus, and then some other modes, vi, which are like positive frequency on scribe minus. You have two sets, and they're inequivalent if the metric is another kind of like killing vector. And I'll assume these things are nicely normalized and the Klein-Gordon product, and the same for the v's. And so there's some, Bogliulo transformations between these guys. So the u's can be expressed in terms of the v's, those with the Bogliulo coefficients. And so the beta coefficient means the u is mixing with the v stars. And that's a positive frequency solution in the past. It doesn't turn into a pure positive frequency solution in the future. Okay, so given that data, so of course you have to solve the wave equation to find those coefficients, but imagine you've done that. Then you also write down an expression for the S matrix in terms of the alpha and beta coefficients. Okay, and that's basically the unitary operator that takes you between the basis here and the basis there. And again, you can think of it in operator terms and work this out. This was done by DeWitt back in 60s, maybe, I don't know. Probably 70s. Okay, but it's a bit tedious. Here, incredibly simple because, okay, so it's a free field. And so we don't have this, of course, and everything is on shell, so we don't have this guy. Well, there's no source there. So in fact, we just had the boundary term. The entire action is coming from the boundary terms. And so we have action is just I boundary, which is just, again, this phi bar plus on scribe plus phi bar plus phi minus, scry minus. And so you just have to find a solution which obeys this boundary data. And if you write it in terms of the mode, it's easy to evaluate these things because these are basically fine coordinator products and those modes are normalized. And so it's really just of algebra, but let me just write a couple of formulas here. So so we can write down one solution that this. Okay, so this has the right boundary conditions, and the B are my boundary data. So that's fixed, but then there's some part which is not fixed on boundary conditions at infinity. But then I have the corresponding thing in the past, and so then I write that as VI plus some unknown guys QI dagger VI star. And all right, so these two things are fixed by boundary conditions, and then the equivalence of these two things fixes the P's and the Q's. And just by taking inner products and literally like one line of algebra, I'm not going to do in front of you, you get something like this: B minus beta transpose B dagger. This is now in a vector type notation. B dagger is first B dagger is beta B, and then you just plug into the action, and this becomes like the alpha inverse -1, B dagger plus 1/2 B plus 1 B dagger. Okay, and so then the S matrix is given by this thing. Just exponentiate that in normal order. That's the full S matrix. So actually, that's one case where this operator version is actually more convenient. You immediately get this is how this S matrix is presented in this operator form, normal ordered exponential, and this lands you right on that expression. Okay, so this, I mean, since solves the free problem so simply, if you want to do some interacting theory in curved space, this is probably a nice starting point as well. So theory. Yeah. Right, so this, so example, a term like this, yeah. So right, so that's saying if the beta coefficient is on 0, yeah, you produce what you start in the vacuum, and there's time dependence, and you produce particle. Yeah. And that's basically the black hole. That's the Hawking. Okay. Good. Now, okay, let's talk more about the structure of this action that one writes on scry. So more boundary action. So so if I evaluate this, say perturbatively, the partition function, it'll very schematically be a sum of terms here. And scry plus will involve various powers of one, schematically like this, M, and then beta on scry minus. And there'll be coefficients here. And so a little bit more explicitly, so the right way to write these things is basically, okay, I don't want to write too many formulas here, but there's some integral over, say, scry plus, which is some integral over the u's, integral over the equals. And then you naturally have u derivatives of the boundary data. because you're integrating over u, and that wants to be invariant. You want a derivative like that, and then some corresponding thing on this would be over this part over scribe minus, and then a corresponding thing over scribe plus. Now in terms of v derivatives, and then the positive frequency part, and then again something we should call a correlator. J. Yeah. Okay, so this thing here, I mean, just formally is some sort of correlator on union of scribe minus and scribe plus. Okay, so now this makes contact with people. There's this whole subject Cartesian CFTs that are reputedly something to do with holographic description flat space. But this will land you on the same sort of object here. Okay, those who want to think of some kind of theory living on null infinity, whether it's the union of the two or what, was a bit unclear what the rules are. But if you wanted to think of this in that vein, you should think of whatever the Carolian theory living on that space is. If you couple it with sources, for the partition function, this is the kind of thing you'd want to get. Okay. So this would be like the bottom-up derivation of that Carolian partition function. And what's done in that literature is taken amplitudes and effectively gone from frequency space to U or V space by doing Fourier transforms, and then extracting these sorts of things. They're just transformed very S-matrix elements. And they have various odd properties. You can try to ask whether they're nice OP and things like that. I think it's still understood, but the structure of those theories is still fairly unclear. Okay. But in any case, this provides a bridge to that. So, right. So the action here, of course, has, I mean, it's say this is evaluated in Minkowski space. Of course, Cap has all the symmetry. This thing has Lorentz on, and it's useful to say a bit more how that. And so, since we're on infinity, mentions it's useful to take some variance in terms of the SLTC description, celestial sphere, and so on, and that allows things to be understood easily. So let's say a couple words about this. You check for Lorentz invariance once you've written it in this form. Okay, let's do the usual thing where we package the coordinates here into 2x2 conventions there. This. And then this guy here goes to the S dagger, where it is a SLTC element. Okay, and of course, if you write this out explicitly in terms of the x's, it looks a bit messy, but it acts very nicely if you go off a large R, off the null infinity. And so, so for example, if we look at these transformations off near structure, we use coordinates where so Z and Z bar, just the usual stereographic coordinate of the sphere. Expressions, but describe the sphere by Z bar. And then this transformation, R goes off to infinity, then you just have that R goes to R over all this F lambda. U goes to U, and of course Z goes to Z plus B, Z plus D, where this F lambda function sphere is given by, won't be very important, but just give it again. Equals squared plus squared. Okay. And okay, so this rescaling of R, right, it's acting like a conformal transformation in the sphere. And so then that tells you thing to variant. So the phi bar transforms because phi bar is a scalar field, but it's the 1 over R component. And the R guy transforms. And so the sources transform. So phi 1 bar up right here. This goes to some, F lambda, phi 1 bar. And then of course, the G's have to compensate for that. And G's here will go to the endpoint function here will go to some product of lambdas, G sub n evaluated at the E lambda. So anyway, it's, correlation in these expressions here, I mean, just comes down to checking that the weights balance. Everything is some conformal weight. And if the weights balance, then the thing is Lorentz invariant. There's corresponding translations, and so it's easy to enforce the full Pointurian. Okay. Yes, exactly. So they indeed want to think of these things as being invariant under Crowley symmetries, but they are basically Pointurier symmetry expressed on that. Okay. Good. Now let me come to where this starts to be more useful. Interesting is when we do gauge theories, we can get into asymptotic symmetries. And so the asymptotic symmetries, of course, have to do with large gauge transformations or large coordinate transformations. And that was, of course, much of the starting point for the whole celestial holography industry of Variant and Company. And one thing to note there that's relevant here is that, of course, when you do amplitudes and so the right connection to soft theorems, and so we do amplitudes in momentum space, and from momentum space you can't really see the full gauge invariance because the large gauge transformations are things that don't have good Fourier transforms, like constant optimal infinity, and so which is derive the soft theorems and so on from Feynman diagrams, but the new insight, one of the new insights of celestial holography is to sort of understand those things from asymptotic symmetries, large gauge transformations. Okay, and so that fits in very nicely with the story. So, for example, if we just have scalar QED, and let me just the formula here. So I'll do this in Lorentz gauge, so I can write down the action. This, and there'll be some boundary terms. And so, okay, so this is the Lorentz gauge. And usual covariant derivative. Sorry. Okay. Okay, so one can again work out the boundary conditions. Same sort of story before the boundary terms. I'll spare you that. I guess the relevant thing is of course, we have this 4 vector there. So when we talk about the actual boundary conditions of the gauge field, I'm going to put boundary conditions in like the radiative components of the vector potential, which are the angular components. So boundary conditions on A, and I'll be working again with the Z and Z bar guys. So these are the Z. So this will go have some R to the 0 type behavior and times some function on U with omega. And I'll put a bar there, and then I'll write it as 0 to indicate it's the R to the 0 components. Okay, so that's the full expression of the subleading parts, but this, and then also the same thing for these guys here. Similar story on both scribe plus and scribe minus, but again, I put boundary 1/2 of the frequency contact on the far past and the far future. And much of what, I mean, just modifications of previous formulas and mode expansions, all that stuff. So won't write that down again. Okay, so if we do that, and compute partition function, again, I'll get some sort of similar structure to what I had over there, but no, well, okay, I'll write this down. So again, I have some stuff involving, if I write everything in Core, you feel like it's a little bit much here, so doing some schematic here, some VUs, and V omegas. I'll only write something on scribe plus, and then we have a bunch of U's of these bar ones, and then U's and then Z's and so on. And string of these things also on scribe minus. And then I have the boundary data. These guys, so now this output, this is A index here. So the A index will be Z or bar. Again, it's the component's tangent to the sphere. And then I'll have some like, and this will depend on some E and I'll call it Y bar, to indicate Y stands for comparing in the field. Then there's now this correlator, which itself is an index. Because I'm just writing a term here with one external photon. Of course, I could write down more photons, but this is enough to get the idea. And these are functions of all these guys. So. Okay, and so again, this thing is now going to be related to some transform of some scalar amplitude. In this case, it's one photon emitted. Okay. Right. Okay. So now we come to the large gauge transformations and the asymptotic symmetries. And so, right. So most of the literature of the subject, the way one gets like the soft photon theorem from more of a canonical framework, phase space and symplectic form and commutators and so on. And it's actually a little bit subtle in that there's some tricky factors of 2 and so on you have to deal with. But in this way of doing it, it's actually quite simple. So, okay, so of course we have gauge transformations. Lambda, and we're in Lorentz gauge, and so that's that condition. And so, right, so the large gauge transformation is a solution of the Laplace equation, but that goes off to has some R to the 0 behavior on scribe. So it acts non-trivially on scribe. And so the solution that does, there's some by solution of this equation, lambda x, that as you go off to infinity, behaves as some function on scribe plus, and then this well-known thing where it behaves as the typical matched guy on scribe minus. So the integration correlated on scribe plus and scribe minus of that. Okay, and okay, so the action with the boundary terms and so on is gauge invariant. It's invariant under this transformation. And so we have this boundary functional, so it should be invariant. And the way it's invariant is then there's a cancellation between, in this case, between a term with one photon insertion and a term with no photon insertion. So it removes the photon, so by other term that are there. And so there's a word identity for that, and then that word identity is in this case the soft photon theorem. So it's completely, once I've written up its formulas, it's really completely simple to write these things down. We can probably see it basically in our head. So I take this term here, and this will vary by this grad lambda term from there. And over there, I could vary the phi's by phase rotations like this. And then for these terms to cancel, of course, here, this one, this term here is one more integral because I have one photon insertion, so I integrate. And so that tells me that this derivative, if I integrate by parts, this derivative comes and hits this guy, or gives delta function. So that I get back down to one left before. And so, right, so if you carry that out, you end up with some equation that looks like gradient A acting on the y, and then we still have this u integral, and so we get the integral of u sample through here. That depends on u's and the y's, and then also you get y's, x's, and that has to equal i.e. Then the amplitude of no photon, ui x hat, and then a delta multi-give delta function. N charges basically delta 2 with the y hat x hat. This is right. This is the photon theorem because it still has the integral over u, and this integral du derivative of u projects the 1 over omega part of this amplitude here in frequency space. Okay, so then this is an easy equation to solve, which is the derivative of something. This is with the sphere equals some delta function, so you can just solve that using the Green's function on the sphere, and you essentially get to the left-hand side is you can say the z bar component of this looks like dz bar of something equals delta function. So you just solve that by 1 over z minus guys. So you solve that, and then you're an expression where in old literature that's the equivalent to the soft photon theorem. Okay. So anyway, so in this case, you can derive this kind of thinking very nice. And again, the point is that this gauge transformation, the act width is just a function on the sphere. It doesn't depend on v to v, and so you're not going to see this if you were working with in momentum space, because you would write this in momentum space. Okay, so that same story should be told for other asymptotic symmetries, and it's a fairly efficient way of writing it. There is, I'll just say words. I mean, there are other things actually are more mysterious. So as if you follow the subject, well, you may know that there's not just a leading photon, soft photon theorem, but there's like a semi-universal subleading one, the low subleading soft photon theorem, which like the omega to the 0 part. And that has to do with, so there's an operator acting on the amplitude that projects out the omega to the 0 part, at least at tree level, one can project this general considerations. At loop level, it's more complicated. But that invariance, or that transformation, I should say that soft factor that you appear there can be engineered into some invariance of this action. Okay, so the fact that the amplitude estimated this property can be converted to a statement that there's some corresponding transformation of these guys that must lead the action invariant. But in this case, it's rather more exotic, and it's some. Let me write down the form letter too. So the weird part is the non-local symmetry. So that, and yeah, so the subleading soft photon theorem implies that the classical on-shell action should be invariant under something that looks like a transformation acting on the asymptotic data, and one piece of it looks like this guy here. So it's parametrized by some vector field on the sphere. So this part here, well, I'll write it, but first, so this part here kind of looks like a U-dependent gauge transformation with gauge parameter given by this combined object. And then I look at the variation of the U derivative of phi, and this has one piece which again looks like the same sort of thing. A, that, but then another part that looks like this. Okay, so there's a U derivative. So this part here is local. So then there's some additional part here, which doesn't have a U derivative. So in fact, the transformation on the phi bar is non-local. So this has to be some symmetry of the action, but non-local character makes it very hard to identify. And in fact, I don't at this point we can't see directly that is a symmetry. So there's some hidden structure in here that's yet to be understood. Some better way of writing the action or something that makes the symmetry manifest. For example, yeah, we don't have to do that. It's quite universal. It has to be true for any potential. There's some arbitrary V of phi, this would be a symmetry of that, so it's a universal. But yeah, it's only a symmetry of the on-shell action and it's acting on the boundary data. So it's not in the form that you have the symmetry. Other we write it in conventional forms. Clear, but I'm sure there's something that okay. All right. So now let me turn to I'll speed up here. The second topic, how we relate this to flat limit. Yes, and part of the story here is this is very story I told so far fits in very naturally with the flat limit. It actually makes it quite to work together very nicely. So okay, so this is, of course, the general idea of getting the flat space S matrix from the flat limit ADS goes way back to the days. And so there's many early papers, Philip Lipchinsky, Susskind, stuff on this as well. Many other go on. List one paper that more recent that discusses this in the context of some of these soft theorems and so on. Is this one from 2021 or that? It's done a different way than I'll describe here. But in any case, so the basic idea, of course, is very, very simple. So we want to ADS, just have some coordinates to stare at. Let's write these down. This is ADS4, and I'll give it scale size L. And let's work in these coordinates. Okay, so to take the flat limit, what we can do is we can write tau is T over L, rho is R over L, and then we can take L to infinity. And if we do that, then this just becomes minus T squared plus R squared, omega squared. Of course, we take L to infinity holding T and R fixed. And what we're doing here is picking out a little Minkowski here near the origin ADS. And right, so then we want to, yeah, so we can make this as big as we want if we take L as big as possible. So there's a big region of flat space to play with. And so we can think of scattering stuff in from the boundary of ADS and arrange things only to collide in that region. And that encode all the flat space S matrix information. So we want to send stuff in there. Come out and we'll collect it. Okay. So that's the basic intuitive picture, which And so if one just asks, so in this limit here, where should these sources come in from? I mean, it's easy to see just from the geometry that these locations here will be separated by delta tau is pi, or very close to pi. The set they have to focus in here near the origin, and so that's means they should be separated by. This sort of configuration here will have some sources here, operators located here, and then sometimes people call this like the bulk singularity type configuration. Okay, so that's a very standard story. So now, how does that relate to other picture? And so the basic thing I want to say is that so we will turn to these sources at these locations, and then we're going to relate it to the boundary conditions here on null infinity. And so the nice thing is that the boundary conditions I talked about before in null infinity map extremely simply onto the sources that one has here. And so the ADS, after a very simple transform, the ADS partition function, the function of sources here, is essentially equivalent to this previous function I wrote down that goes to flat space S matrix. So there's an equivalence between ADS partition function with sources and S matrix generating. That's the upshot of the discussion. So how do you show that? You carry that up. So for example, we want to turn on boundary sources. We want to work with the bulk boundary propagator, and so that's in global coordinates. So this, the prime coordinates are now the boundary, and prime one is living in the bulk row, and then I'm describing the points on the sphere by x hat. There's some important epsilon here, and so if this was a general mass field, we have the usual expression m squared L squared is delta 3. We have that, and I'll just take a mass field, so I'll set delta equal to 3. Okay, and then of course, so then what that thing does for a living is it produces a solution of the bulk motion if you integrate over the boundary against the bulk boundary propagator. Let's call that prime. Right, this produces a solution of the bulk equation of motion whose boundary can be specified by the boundary source J. Okay, so then you want to ask, okay, so if we want to scatter things in, we want to have things come in as plane waves there, and so you should ask what kind of source would produce a plane wave. And this was, again, look back, I think there's a paper by Gary Giddings and Panadonias that does this. Possibly others as well earlier, I don't know. But what you can do is let's integrate, first of all, the source. I want to have an incoming plane wave. So let me integrate it over past this region. So this is, say, going from, so I shall extend some region here from like minus pi to 0. So I'll integrate pi to 0. We'll see that this localizes in a second in the flat space limit. And I'll introduce a phase and integrate that against the bulk boundary propagator. Like that. And okay, so then you can, what is a, so this is at some fixed location of the sphere. I'm just integrating in time. And so then you can take that integral and put boundary propagator here, and then ask, what does that look like in the flat region? In other words, write the coordinates like this, and take L to E, and that will tell you what the solution looks like in there. And it's a fairly simple thing to do. Yeah. And do this by simple points. Actually, do this, look up some factors of L in there. I'll do this in detail. And then do some saddle point, and then the saddle point localizes, in this case, tau prime gets localized to minus pi over 2. That's where stuff happens here in the design. And so then this thing just ends up being ends up being I over, this is in the flat region, L omega squared e to the I p prime dot x, where this p prime vector is given by xn. So it carries the frequency omega. Its direction is antipodal to the where it came from. So it's pointing in that direction. From here, it's given by this typical point of the sphere is direction. Okay, so this gives you the desired plan. Of course, you can do the same thing here. The source is over there, right? In that case, you can integrate from 0 to I, and then there'd be corresponding saddle point near 2. Okay, so then you need to learn to see this geometry coming out in this limit. And okay, so that gives you one plane wave, but the generic thing that we want, of course, this is just plane wave with one momentum. Of course, by the fact that I only put in the source at one angular location. General thing, of course, is integrate over the sphere. So, so more generally, we'd have, and notice, well, I'm going to take the omega. So more generally, have like say positive frequency x integral over the vector 3p prime positive frequencies. So this is stuff your frequency source, and I'm integrating over the time strip that I did here for the source in the past, and minus pi to 0, but I'm also integrating over the angles. Integrating over the angles then correlates to the direction of the momentum, and I had a general superposition of plane waves here. Right? If I choose a source with prescribed angular dependence, I get some arbitrary collection of plane waves. And then before I told you we had a general plane wave expansion, how to read off like the 1 over r asymptotics, and those 1 over r asymptotics were the boundary data in flat space. So I can just repeat that analysis here. And that will give me a relationship between the boundary data in the flat space and this. And so, if we do this, and a little bit of algebra, you will find that this means that what I'm calling, this positive frequency data on scri minus this function is given by this simple expression. This, well, you did around pi over 2, but then there's a v coordinate here. So it's a data, it's the source data in a little strip of sort of width 1 over L around around this control minus pi over 2 point. Okay, and then a corresponding thing, of course, for the data on scri plus, very similar. This guy. Okay, so right, so the picture then here is we have this, so there's sort of two little strips here, and this is sort of like delta t is essentially 1 over L, and same thing over here. Delta t L. The two things are separated by the t equals pi. And so sources live in this region, and they get sort of directly so you sort of take this and extrapolate it out here. There's kind of a direct imprint of the flat data onto the ADS data. So that means then, okay, a little bit more work to show that. So the action, of course, the full action in ADS is the action for the flat. There's some action from the exterior region, but I'm assuming I have plane waves that are basically free fields here, and so one can show that that takes care of itself. That includes, for example, the boundary terms I talked before. And so what that boils down to then is that this that partition function for the asymptotically flat space region that produces the S matrix in terms of these guys, the x hat minus the x hat in terms of those sources there. I mean, that's equal to the ADS partition function in terms of J plus and J minus, where the map is this thing. Okay. So that's a very direct relationship between two things. And now, so we came back to this, coming back to the story, the sort of Carolian type situation where people have directly, when they want to say, okay, scry minus, scry plus, and then some sort of Carolian QFT that lives on of these two things. And then there's a question of how, so the correlators are some correlations between the two, but you're supposed to couple those two theories together. How do these two things talk to each other? And so when you bet this in ADS, I mean, you get something you may not like to get, but this is what you, I mean, there are two, so the scry minus and scry plus are basically being imprinted on these two strips here in the large L limit. And it's clear, obviously, they're correlated by, I mean, the evolution of the CFT between the two times. And that's not, of course, a simple thing. If you wanted to do that, you'd have to solve for the time evolution. Okay. So to the extent you could try to make sense of a CFT, in this CFT dual space that lives on scry minus, together just to put in the evolution, CFT evolution between those two. So okay, so one same thing goes through then in the case of gauge theory. So just extend the labels here. So there's an imprint. We work at the boundary conditions of the gauge field here on that space. Those just become the sources, the gauge field ADS boundaries. It's a little complicated expression, but is the same. And so that means then that the asymptotic symmetries, like the large transformations that act here on the flat space, one can extend those gauge transformations out to the ADS region, and they will act as large gauge transformations acting on these two strips. And in fact, the antipodal identification between here and here extends out to the antipodal relationship between the boundary data here. And same for the Lorentz transformations and so on. Lorentz transformations here can be correspond to what look like sort of Lorentz type transformations acting in strips. And so all of the symmetries in the flat space are apparent here in the CFT, provided that you restrict your operators and your sources to lie in these little regions here. And of course, they'll only emerge in the large L limit, finite L limit that is not exact. But so it's really interesting. I mean, one could probably do in the CFT, of course, it would be interesting to, if one could carry this out, I mean, have a situation you have operators in these little strips and evaluate things and take them out to infinity and see this enhanced symmetry come out. But okay, so let's see something else. So you want some additional structure inside that button, a little black hole or something. Yeah, right. So then, of course, you'd have to look at even as a background. Yeah. So right. So I mean, of course, I should look at some starting point would not be global ADS that you wanted, and you'd have to write down a corresponding solution that doesn't really fit the flat space limit. It doesn't dilute away entirely. It's an imprint, but yeah. So then, I mean, of course, then you'd have to know how to encode that in ADS. that trivial solution there in the boundary is a state or something like that. So here I have in mind doing, so again, coming back to the cap thing, the natural thing to do here is to cap off these guys here, because we're doing the, we don't each want to study estimate one scattering, one have the vacuum here, vacuum there. And so, so now I might entertain putting in some sort of operators here and so on to create some sort of thing in there. So I suspect that's possible. It could perhaps get complicated. You have to thing in the center there. You have to transport that information off the boundary. Okay, I think I'm going to just stop there. Anyway, so just to summarize, yeah, so I think I think this is good for asymptotic symmetries. Again, it ends up this functional. I mean, you could have discovered it this way. Just embed flat space in ADS and know about the ADS partition function. You very quickly transport that, and you're producing this thing I studied there, and other generation of gravity and massive particles and so on. Complicated, but okay, I'll stop there. So what is the observable that you compute there? Yeah, yeah. Oh, I see. Okay, yeah. One is more. Yeah. Yeah, yeah, yeah. Yeah, it's right. Different contours. Yeah. Yeah, yeah, I've thought about that. But that's yeah. This is a path integral with different contour. Yeah. Right, right. Yeah. Right. Oh, yeah, yeah, yeah. Of course, right. Right. So, of course, in the QED case with the massive particles and so on, there are also infrared divergences. Right. So there, of course, the starting assumption I said the plane waves that first place you calculate things. So yeah, usually you should look at. Haven't worked this out. I mean, there's a modified something called the Coulomb interaction. So I think they want to do that. I'm not sure if it would be any advantage to the normal procedure, but yeah, modify it. Right, right. So L is acting like some IR regulator, and yeah. So if you, I mean, of course, you only see this when you go through loop level, but yeah, I mean this is produced. I mean, assuming what I've done is it should what I've done is correct. If it doesn't diverge, I did something wrong. Yeah. So this is some sort of IR regulator, which I mean, I don't. Perhaps it's a useful IR regulator from that point of view. I think some people have explored that perspective. I'm not sure, but Yeah, yeah. You're right, right. So you want to correct, right? One, all the interactions here, and you have to worry about are things like this. Yeah, so this comes down to um, wave packet type questions. Um, and what I think tree level should be fine. I mean, I don't think you'll run into any problems with the tree level, but I think the real issue are things like can you show that these are all suppressed? And I think Giddings had some old papers back in the day where he was saying there are actually problems. You can't actually write down good enough wave packets, but I think that's I think a bit of an outlier position. But to be honest, hasn't really been checked explicitly because you have to do this. You'd have to do some loop. It combines both the unpleasantness of having packets and loops. So it's not something we can easily do, but it's yeah, it really should be. It really should be checked whether you can really ignore all the interactions in that outer region. Um, of course, oh, for tree level, Mellon space. I mean the Mellon approach. Yeah. Mhm, 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 mhm. Yeah. Mhm, 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 mhm. Yeah, yeah. Here it's all everything to do is a wave packet because I mean from the construction we take the bulk boundary propagator flat limit. It's clear that if the vertices are restricted to the region, they'll refine the diagram. Built in. The entire question is whether there are nice enough wave packets that's there's no overlap between the external guys. Yeah. Yeah, that does not change. Yeah, so that imply. I mean, if you just I can just take that transformation and then use this dictionary here, and it'll now be a transformation of sources. So that's again one of the important things about this is that things are asymptotic. So in flat space, you're doing transformations on phase space in terms of the data, but those get transported over here to sources. And so you're asking about the variance of the generating function of the transformation of the boundary positions of sources. So yeah, it's some non-local thing, but again, it's only going to be there in the large L limit. So now you have one more dial that complicates matters. So um, I have a hard time seeing that's going to make it hard to see that if you don't understand it here, you're going to understand it in that case. But I have thought about it. Yeah, yeah, right, yeah, right. CFD is very special at these locations. That this bulk point singularity configuration symmetry there. Yeah. Mhm. Extra symmetry for a restricted class of correlation functions. So you're for a symmetry of the full CFD, only for correlation functions that are like, operators restricted to this window in large